we're going to try to record all classes just so that you know it. And it's that folks online can reference them, but it ends up being a reference for you too. So cheers. Okay, just open this puppy up. First, just a quick poll. Has anyone coded before? Sweet. Well, I was about to say, I know that you have. I talked to you yesterday. You can hide. Okay, cool, great. That's totally fine. This class assumes that you know nothing about coding, and aims to take you from there to knowing something about coding. So it is fine to start from nothing, because that's the point. All right, let's get this shared. There we go. All right, sweet. And am I this cool? Yes, it is. Sweet. Okay, so welcome to programming. In this class, we're going to be using a language called Python. We're going to try to maximize puns, because Python lends itself to puns. So if you don't like puns, deal with it. Sorry. A few things of introduction for anyone who doesn't know. For anyone who doesn't know me yet, it looks like, oh, so this is in your way. Actually, before we get to there, if you have a laptop, grab it out. If you don't, make sure that you bring it. It's a programming class, so expect to use it. We're going to get something downloading. I guess that's going to have to be your desk for today. I'll see if I can work with Jim to get another one rolling for you. Sorry about that. Brandon. If you can go to that, if you can go to the link that's up on the slide where it says tinyurl.com/python3-setup. I just want to get Python starting to download while we're going through the introductory material. In other words, I'm going to stall while it installs. So what that link will take you to is a website that declares itself to be the homepage of a thing called Anaconda. Anaconda, to start off the puns, is Python with a whole bunch of other packages and software who's with it. So think Python, snake, Anaconda, bigger snake, eats the smaller snake. You get Anaconda, you get both. Yeah. No? Okay, cool. So you go there. If you scroll down the page, eventually you'll get to where it says Anaconda installers. Since you all have school laptops, it means that you all have Windows. It also means that you all have 64-bit machines. So grab the 64-bit installer for Python from the list there. Should look something like that. Download it. Eventually it'll download. When it downloads, get the installation started. So just wait for everyone to get to that point. Well, so everyone has the installation started, we'll move on, because it takes a little bit to get there. So everyone got it going? Yes. Great. Okay, sweet. Onwards and upwards then. So while that's installing, for those who don't know me, I'm Brother the Marius. I'm a Franciscan friar, in case you're wondering what the heck's up with this. I'm also a total nerd. If you want to talk about anything related to flying, I am totally down. Or hiking, all that sort of stuff. I'm in. Most of my work's been in small rotorcraft design and analysis. So if you see a whole bunch of aircraft examples, that's definitely where I'm coming from. If you don't like planes, well, you will soon. So that's that. If you want to find me, I believe it's unlocked, but also just knock. If you want to find me, my office is Science Center 027. So if you know where the conference room is on the bottom floor, I'm right next to it, or the door, or better known as the door that leads to Adamucci's and coffee. I'm right next to that. Please stop by any time. Not sure what Jens guys' comfort levels are with like being in person and such. So if you need to not be in person, we can work out how to do a Zoom call. Else, just drop by and we will make the dream work. I'll definitely be there between 9 and 10 a.m., which is called Monday through Friday. I also live there most times, so just drop by. If I'm there, I'm there. My class schedule is sitting outside my door. So reference that if you need to know where I am if I'm not there for whatever reason. Grades, because everyone likes to know about grades. So how I work things is like this: 30% homework. There'll be a bunch of projects in lieu of tests, and in a final project in lieu of a final. The aim, as I said, the aim of this class is take it from knowing nothing about programming to developing a tool. In this particular class, we're going to work on a ideal gas law compressibility factor calculator. Don't know what that is? It's fine. We'll get there in a month or two. So that'll be your final project in lieu of a final. In terms of homework, pretty much just get in by the start of the next class. If not, that's when I start taking points off. It's fairly straightforward though. If you, for whatever reason, cannot get in by the next class, you have some crazy thing that makes you take time off, whatever that may be. Just let me know by by at least a day before the homework is due, and we can work something out. If you need any help, please just drop by my office and we'll work through it. Cool beans? Any questions? Great. Also, can everyone hear? Can everyone hear me all right? Those in the back? Okay, cool. Sweet. All right. Last thing. This PowerPoint is online, so you should be able to get to it. Here are a whole bunch of resources for coding in Python. I've used most of them at some point in life. If they're all, they all have some perk to them. Some just kind of explain the basic commands like the Python cheat sheet. The manual tells you all that you wanted to know, and then about 10 times more than you wanted to know about any commands. And you have little things that let you just try different commands. There's a whole bunch of useful stuff out there. So please feel free to use it. And please read the syllabus. If you haven't read a syllabus before, this is the year to start reading syllabi. Okay, because in there's all the anything that you ever want to know about what happens if I have to miss class, or what happens if the instructor gets sick. It's all in there. Okay. The long and the short of it is that classes will be available via Zoom. If you can't make class for some reason, I expect you to be on Zoom unless you really just can't do class at all. And then, well, that's why we record them too. If I get sick, we've kind of worked out a network of backup instructors and such, or like happened for this guy. He helps. He doesn't help. He works for the group called TopCon Positioning Systems to make high-grade GPS units and survey other pieces of survey equipment. He came down with coronavirus about a month ago, so he locked himself in his basement essentially until he got over it. He just provided call-in help from his basement for 2 weeks. So if all else fails, you can still get in touch with me, and I can still get in touch with you guys as long as I'm not like in a coma. Okay, cool. All right. So on that happy note, I just want to make sure that we're good online. Great. All right. So with that, let's talk about computers. Any guesses when the first computer was? Anyone? Anyone? Yeah? Before that? Yeah? I forgot I gave you the answer. Yes, 1820. It was that. It's called the Babbage difference engine. And I bring these old computers up because I think that not a lot's changed in the past 180 years. And there's a lot that we can learn about current computers by looking back at old, by looking back at old ones and kind of getting the bare bones of what coding is. So back in 1820, there's a guy by the name of Babbage, and he wanted to do hard math problems, pretty much. It's like we've been able to multiply numbers for a very, very long time, right? Well, at least several hundred years. But it's tedious, it's long. Be nice if there was someone that would do it for us. That sounds like a reason to make a calculator, right? So all this thing is a big old stack of gears. There's that computes your thing, but it's driven by this stack of cams here. So I set these cams to represent my math problem. So I can set up a number here, and it is the same thing as saying 586 times 273.6. So then I turn that crank. Those cams drive all these gears, which process through to this thing here, which literally writes an output, and that's it. That's the entire thing. It can multiply, it can divide, it can do logs. That was actually the purpose of this machine, to crank out logarithms before you had calculators to do it for you, because logs are freaking hard. I mean, you call for log 10 of x. You say like what log 10 of 50 is. It's like 10 to the what power is 50, right? Like what the crap is that? And that's what these machines did, because else, like, if I was trying to figure out how to problem by hand, it was some sort of engineering design work, I'd be spending forever trying to figure out the friggin' log of 50 when I could be designing something. So that's why they made this. It actually ended up not working because in 1820 you couldn't make gears precise enough to make the machine work, which is friggin' awesome to me. Like the fact that you could come up with a machine that you actually couldn't use because you were so far ahead of your time is cool. But they actually did build it in 1850 and it worked. Fast forward to the 1940s, and you get Colossus. This is one of the early computers. It was before ENIAC, which you might know from like British code breaking stuff. Colossus was used to compute tables for artillery gunners. So you want to know what angle to set the gun at, how many things of powder to throw into the gun, blah blah blah. Someone would crank through a whole bunch of different problems, say for wind speed, elevation, the differences, all that sort of stuff. Put it into a book and you just reference that. That's Colossus. And it has a lot of the same things as the what's called Babbage machine does. It's just as confusing. I mean, if you know how to set up gears, I'd love to know. But if you know how to set up this, I'd be pretty freaking impressed. Just saying, you're physically plugging and unplugging parts of the machine together. That's the coding for this machine. So if I want to set up a problem, I flip a whole bunch of switches, I plug and unplug a whole bunch of things, and that represents the problem that I want to solve. And it represents my program. So when we look at this, something that you might think of is, it'd be really nice to not do that every time. Like if I just had my program stored somewhere, that'd be really, really nice. And that's where punch cards come in. So this is the first kind of means of external program storage. And this is where we start getting into what coding really does. So how these things worked is you had a card. It was just a little piece of paper. It was just a little piece paper. It had 85 rows on it. 85 columns. Each column was, you could punch out a number on that column, and that is one, you might say, one letter of the program that you want to write. That's it. So as you might imagine, this is a pretty small bit of memory, right? About 5 megabytes of code looks like that. My mom said it was the first time that she had seen a grown man cry when he was carrying his cards down to the computer to run it. He tripped. They all fell all over the floor. They're all out of order, and now they mean nothing, right? That was coding with punch cards. So it worked. Not the best way to do it. So where do we go from there? We're still trying to get this kind of permanent memory that we can just stick into a computer and say go and have it run. So the next step was something called the Williams tube. So if you have someone like me who's a dinosaur who like was in the age of cathode ray tube televisions, seen those like really deep ones. Okay, thank you. There's someone else here who remembers. So those big glass television sets or computer screens work by a electron gun in the back shooting an electron at the screen, and the screen glows. It does it really, really, really fast. So this is that. You have a little electron gun back here and shoot electrons. And then the face of this, you could store charge on. It would glow in a way. So this is the front. This picture to the right is the front of this tube here. And the bright spots are where charge is stored, and the dim spots where charge aren't stored. And they had a way of kind of scanning across it and figuring out where charge was and where charge wasn't. So same as with the punch card, you know where punch is and where punch isn't, right? This is kind of the root of computer memory. Looking at a thing and saying, is something there or not there? Is it a 1 or a 0? If you want to think in binary terms. And this is how we kind of have to think for a lot of stuff in this class. So this worked, but as you might imagine, like you have to have physical space between the dots, blah blah blah. It wasn't perfect. It didn't stay charged or uncharged forever. It wasn't the best, but it worked, and it was a permanent memory. I could store a program on this, and then read it later, so long as I kept up the charge and all that jazz. So the next step was to physically sew it, if you will. These black rings are all permanent magnets. The copper wire is just that. It's just wire, and it's put through all these magnets in a very particular way. If the magnet's facing south to north as the wire goes through it, that's a 0. North to south, it's a 1. Same as the punch cards and the Williams tube, right? Hey, there's a yes or a no. It's one thing or another. And if you weave it through, this is what 8 bytes of memory looks like. This micro SD card is 8 times 10 to the 9th bytes, just for reference here, so we keep sense of scale. So this thing worked, though. It's called this wire mesh. I mean, it freaking worked. You had long-term memory. There's no way that you can change this because it's a permanent magnet and there's a wire through it. So this thing, you could stick it into a computer and not change it forever, and it'll work a billion years later. Awesome, unless you screwed it up. Then it just sucks because you have to rewire the whole thing. So the next step in computing, and this is where it's called we start looking at it more, is this is a great way to have memory, but it's not a great way to code. It's actually a really sucky way to code. I don't want to code like this. I want to type in a word and have it mean something. And that's where COBOL comes in. So that's the first human readable programming language. By human readable language, I mean, I have a computer, I have a keyboard, I type in some words, I see it come up on the screen, and those words mean something to the computer. Ultimately, a programming language is just that. For us, it's a language that we use to communicate with a computer. So when you approach coding, I want you to think of it as a language. It's something that you have to start to be able to think in, write in, read in. It's a language. The computer is also also knows that language. At least it will once Python finishes installing. It's using that language to convert your commands into code that it knows to run, which is binary, machine code. That means take a value X and add 1 to it. I don't want to code in that. I want to code in this. So that's why we have these translators, if you will, of which Python is one. There are a whole bunch of others: C, C++, Ada, Java, Haskell, C#. I think someone said they program in Ruby. False. There's a crap ton of programming languages out there. We're looking at Python because it's really good for what we do as engineers. It has a lot of different packages to it that help us do what we need to do. So if I look at your usual whole Python structure, this is kind of what we're going to be working in this semester. You can think of part of it like algebra, which we store values as variables. Something to get through your head though. Everything on the right gets stored on the left. So this puts 100 into this variable here. Then you can do math with those variables, and then spit some output out to the user. Now at this point, I'm going to pause. Has Python finished installing? Have I delayed long enough? I hope it was an interesting delay. Cool. So if it has installed, I want you to go into your Start menu. And you should have an option. Let's see if I can play this game. You should have an option to I just want to share my screen. You should have you should have the option to search for spider. It's called search for spider. SPYDER. Folks find that. Should look something like that. Just SPYDER. Sorry, I can't make that one bigger. Everyone finding it? Yes, no, maybe. And when you open it, eventually it'll look something like this. And it takes a while. And it takes a while to open. Here we go. Here we go. So it should look something vaguely like that. Everyone got something that looks like that? Sweet. Okay, so welcome to Spider. I think you might have an extra window on this side here. Yeah. Yeah, that's not what you want. Okay. Get some nice knives from there though. Anaconda. Okay, so you got that. Where's? Oh, that's interesting. Oh, there it is. And you already opened that, right? And that's run. That's done. Yeah. Okay. It didn't install it here. I need to install that. So I'm just checking to see if it is installed. That's strange. Okay, let's see if it sees it. It should have popped up in there if it was. See. Users. Oh, I don't think it's installed. Yeah, now it's going. Once that finishes, you'll be able to catch up. Okay, so Spider is called an IDE. It's an integrated design environment. It's what we'll be using to code in Python this semester. The only caveat I have to that is that for whatever reason, Python never has a problem on anyone else's computer except for mine. So if I use it, my computer will probably crash. So I'm not going to be using it. What I'm going to be using is the command the command line. Will that matter for you guys? Not really much at all. It just means that my code will be on a black screen and yours will be on whatever color Spider is. Okay, so Spider, the kind of neat thing about it and why we are bothering with it as opposed to the command line that I'm using. Pull this up. There we go. Is that it's really helpful. If you look on the left-hand side of the screen, it's just a big empty space. Has what's called might have some text on the top. It says like UTF-8. What's called author, blah blah blah. So this is where you write code. That's called that section on the left. That's where you'll write your programs. Got a green go arrow at the top of your screen. That's how you'll run them. It's pretty straightforward. The stuff on the right hand side. At the top, you have a couple windows, might say Variable Explorer, File Explorer, Help, all that sort of stuff. That can tell you what's going on in your code. For example, the Variable Explorer, every time that you run your code, it'll tell you what the value of each variable is that's in it. So that can be a kind of just a useful thing to see if variables are what you think they are. Then at the bottom thing here, where it says IPython console. What that is kind of a live version of Python. It's called a Python interpreter. If you just want to run a command, you can write the command in here and see what it does. As opposed to in the left-hand side of your screen, if I type it in there, I can write as many commands as I want, but then I have to run them all together. Here I can just try one thing and see if it works. If I go down into the IPython console. Does that make sense to everyone? Okay, great. Okay, so it's a kind of handy thing. Did it finish installing? Okay, sorry, it's going to be there for a little while. Let's try to use Spider. We'll get you up to speed in a minute, Jenna. So if you go into that left-hand window, delete everything that's there, and we're going to start with our first bit of code. So whenever we write, yeah. Okay, let's have a look. Ooh, that is not good. Sorry, your screen. Okay. Yeah. Yeah. Okay, so did all that. Okay. So let's have a look. I am looking for C drive. Users. So okay, it's all there. So Spider. There you are. Yep. Anyone else having a problem pulling up Spider? Oh, no. Great. Okay. Yes. hit your start menu. Assume that you've installed it. Oh, and there you go. Okay, so once you got Spider up, it can take a little bit to load. Go over to the scripting window, which is on the left. Highlight everything that's there and delete it. So when we code, there are, there's two ways of writing commands. One is a command that the computer will read. The other is a command that the computer will actually ignore completely and only has value to you. First thought might be, what the crap is that for, right? And the point is, you might know when you do something in a program, you have to go back and change it later, or more often than not, fix it later or expand it later. It's good to know what that bit of code did in the first place. And remember, this is a language, so you're trying to read a foreign language and interpret what it means in the context of like maybe 100 other lines of code. So it's good to leave yourself with some notes that you don't care about the computer reading. So these notes are called comments. You mark a comment with a pound sign. Any line that you start with a pound sign, the computer will ignore. It will not run. It will not think. It will not think about anything that you write after that pound sign is entirely for you. So it's just for your notes. So let's start this program with two lines of comments, just saying what the program's going to do. And what it's going to do is write hello world in the IPython console. So start by typing that into your code window on the or scripting window on the left-hand side. And how we're doing this is essentially how all codes are going to run. They just get bigger and more complicated. Okay, so once you got that in, now we're going to write write something and tell the computer to do something. So for me, it's line 4. It honestly doesn't matter if it's line 5,000 for you or line 2. On the next line, I have written print. That doesn't really help you out that much. Sorry. On the next line, I've written print. It has an open parenthesis. It has a closed parenthesis, and it has some quotes with some text in the middle of it. Print is a command that tells the computer to do a very specific thing. In this case, print says write words or write whatever is inside of these parentheses here into the IPython console. That's what the print command does. And we're going to be messing with how it does that, but at the root of it, that's what it does. And this is the same for almost any command in Python. There's a certain function that they do, and they usually act on whatever is inside of the parentheses making up that command. In this case, we're going to tell print to write hello world. You have to put that in. You have to put that inside of quotes. Else it doesn't know that it's a word or a bit of text that you're trying to write. So make sure you do print, open paren, quote, hello world, close quote, close paren. And that's what you call it. And now you've told the computer to print those words to the IPython console. Everyone got that? Cool. So if you hit run, that green right-facing arrow, you should see it pop up in your console window. Everyone got it? Sweet. All right. So that's your first code. Everything else is Everything else is going to be a piece of cake now. Yeah, sweet. Or pie if you like pie. I like pie. Anyhow, so that's what's called. So everything else we do is going to follow those same kind of steps. You write some comments so that you know what's going on. You write in commands, and you go from there. The trick is just the commands get more interesting and more complex. You might think if this is a language, if the only bits of language I knew were nouns, I couldn't write sentences. Or verbs, I couldn't write a sentence. I need other things too. So we have a bunch of other parts of speech, if you will, that we're going to be talking about in this class that we'll need in order to write useful programs that don't just say hello. If you've ever learned a language before, I don't know how learning a language was for you. I know that it was very difficult for me because I hated memorization. But how I had to work through it is just use it. And that's how it's going to be here. You just have to use the language, learn how to speak it, learn how the computer talks back to you. I know that might seem weird. Computers actually do talk back to you. They're called error messages. So we'll learn how to kind of interact with those and go from there. So yeah, we'll talk about that a bit later. Cool. So let's move on to the fun stuff. So there we go. Share that one. Great. All right. So as we start getting into programming and kind of expanding our sense of the language, kind of our first stop are variables. This is how we store information inside of the code. There are a variety of types. We're not going to worry about that too much. If you want kind of a way to think about it, think about Excel. You've all done math in Excel at some point, I hope. Okay, cool. So if I'm in Excel and I want to add two numbers, I click one cell. I guess it's multiply. Sorry. I multiply by the other cell or add the other cell, right? Which called these are effectively variables. Whatever's in cell A1, I multiply by whatever's in cell A2, right? I can change whatever is in A1 or A2. I can change what's stored in those cells. Python just makes it a little bit nicer because you can actually name those variables. Like if A1's length and A2 is width, well, hey, I can just call them length and width. Heck, I'm done. Makes life a lot more straightforward when I'm trying to read what I've written and make some sense of it. I don't know if you've had the experience of going through a massive Excel equation, going, what the crap are all these? That's what's called. That's something that Python kind of helps out with. So this really is just an expression of algebra in a sense. We have a whole bunch of variables. We get to pick the values of the different variables and go from there. Variables are just placeholders for numbers. If this seems like it's too straightforward to be true, you're right. So the trick is 532.600.6325678. How do you express that as a binary number? Because computers think in binary, right? How do you express these things as a binary number? And because that, we end up having some limitations and such that actually end up being a problem later on. We also have a couple different variable types. So we have number types and we have character types. Integers and floats are numbers. And these are good terms to keep in mind because eventually you will get an error message saying you're trying to do math with type str, which is a string, and it's saying I can't do that because it's not a numbers. These are good terms to keep in your head and to write down somewhere so that you can think of them later. So Python can do math with numbers just fine. The numbers that it recognizes are ints, also known as integers, and floats. Those are the numbers that the number types that it knows. It can't do math with characters, but they're known as strings. Hello world, that thing in quotes, was a string. It's not a number you can't do math with, but you can put anything else you want in there. So what is this? So who cares, right? Well, this is why. So when you want to store a number in binary, you store it as a string as a set of ones and zeros, right? Let's see, what's going to be the easiest way to do this? It's going to be this. So if I wanted to store the number 8, it would, let's see, 1, 2, 4, 8. It would look like that. In base 10, where this would look like 1,000, that first number to the right, that'd be like 10 to the 0. So that'd be how many ones there are, right? How many tens there are, then how many hundreds there are, how many thousands there are. So that looks like 1,000 if I wrote it in base 10. Binary, however, is also called base 2. So instead of being 10 to a power, be 2 to the 0, 2 to the first, 2 to the second, 2 to the third. So I have no 1s, no 2s, no 4s, and 1 8. So if you ever wonder about the 8's place, so I started talking about that. This is I'm talking binary. So as with what's called like regular numbers, I'm limited in how large of a number that I can express by how many places I have to express it in. And each digit takes up room in memory, right? It takes up 1 bit of memory. There are 8 bits to a byte, 1,000 bytes to a kilobyte, million bytes to a gigabyte, so on, to a megabyte, billion and a gigabyte, so on and so forth. So there's some finite amount of digits that I can use in every binary expression of a number that I make. And the computer says, okay, then I'm going to make these variables like an integer or a float. And I'm going to give them so much memory to work in. It can't make them infinitely large because you don't have that much space. So it assigns some amount of memory. It assigns 32 bits for an integer and 64 bits to a float. And that's how much memory, that's how many ones and zeros you have to represent each number. As a result, that means you have upper and lower limits, right? Like if I only have 32 bits, that is called 2,147,483,648 is the largest number that I can store in 32 bits with a positive and negative sign at the front. That's the largest one that I can store. And if I try to store a larger one, the computer will actually start to yell at me. So let's see what that looks. Let's see what that looks like quick, because this is that you will run into sooner or later. And let's expand this a little bit. Okay, a little bit more. Okay. So if you typed in your IPython console, it'd do the same thing that I'm doing right now. Again, Spider causes my computer to crash. It seems like it doesn't have any problem on anyone else's. So that's why I'm doing this. So let's do this. I'm going to have a variable, and you could actually do this in in your IPython console too, if you wanted. I'm going to give that variable a value of 999. Okay. So I say one variable equals 999. Everything on the right stored on the left, right? So when I hit enter, one variable now has the value of 999. Don't forget the underscore there. If you just put a space, it will, which is called Python, will not be happy. Okay. Then I'm going to say output. I'm just going to make up another variable. That's going to be equal to one variable. I'm going to raise it to a power. In Python, that's 2 asterisks. Okay. I'm going to raise it to the 1,000,000th power for kicks. And we'll sit there and, hey, it actually, should call it. It got that one. Sweet. I have to think about that for a while though. Wow, it really has to think. It really has to think about that. Wow. Okay, I'm impressed. Last time I tried that, it did not like it at all. There we go. Sorry. Make one variable equal to 999.1. So just go back to your console, hit that, and then raise it to the 1,000,000th power plus 1. You should get an error, and when you hit enter, you should get an error that looks like that. The commands end up working out for folks. Remember, we're in the IPython console, so we're in the thing in the bottom right-hand corner. If you typed everything into the code window, it'll work there too. You just have to hit the green run arrow. So everyone should get that error there that I got, where it says trace back most recent call last, file stn, line 1 in module. You guys all get something like that? Ah, it's because you did it in there. Yeah, hang on. It's running. You have to break that. It's trying to run. Oh, okay. And it's going. I don't know what's going on. Yeah, just open that puppy. Let's open that puppy up again. Yeah. You can do it. You can do it in either. But do you see how there's a green line? Yeah. If you see that there, it means that it's still running whatever you did last time. Yeah. Yeah, it has to be to something like that. Yeah. Yes. Work now? Or errored out? Okay. Ah, yeah. It's so you see how you got that? So that means that it's still running that. It won't stop running that until you get to a new line of in 4, in 3, in a number. It's probably the easiest way to get through it is to close that out and open it back up quick. Cool. Yeah, just close and reopen it. Got it? Yep. Yeah. So yeah, so just close and reopen that. Which call you guys got it in the back? All right. Yeah. Yeah. Okay. Yeah, so you see this guy here? Yeah. Because it says this, and it's not to a new line that's just blank, I think with in6 or in5 or whatever, that means that it's still running whatever you had in there. So Control C usually gets it out of there. It looks like it's pretty stuck. So just close and reopen it. All right. Yeah. You got the right error. you got the right problem. You're fine. So make it 999.1. And don't bother about line 3. You don't need it. Okay. Yeah, it'll cause the same error. But then, yeah, just hit the green arrow, and after a little while, it should go, what the crap are you doing? And when it says result too large, overflow error, what it's saying is that variable can't hold what you're trying to put into it. So when we look at these error messages that appear in your IPython console, these would help us to know what's going on with your code. So in this case, this first bit where it says trace back file blah 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 blah, don't worry about any of that stuff. Where it says run file blah 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 blah, that just means it's trying to run the file that is at that path. Okay, you can ignore all of that. What's most important is what comes at the end into that message. In this case, it should say overflow error, result too large. What it's trying to say is the number that I'm trying to stick into that variable is too big to stick into that variable. It takes up more memory than that variable has to spare. Okay. Why it didn't work as so why we had to do 999.1 is because I had to force it into a variable type that I knew that it'd be easy to force and overflow in. 999.1, the 0.1 is the important bit. It means that there's a decimal value to it. And if there's decimal, it's a float. If it's a float, it means that there's some really interesting stuff going on. In particular, hey, come back here. Let's have a look at this. I'm going to say output is 10 minus 0.1. The answer to that is what? 10 minus 0.1 is, say again? Or just 9.9. Yeah, 10 minus 0.1, right? That is 9.9, right? Yeah, I'm not crazy. Okay, so I'm going to do that. I'm going to print that output. I'm going to do it to 17 decimal places, okay? Oops, sorry. Oops, that's why. Duh. What the heck's up with that? 10 minus 0.1 is 9.900000000000036. What the heck? The computer screwed up math. Why are we trusting this to do anything? And this is another thing that you might see, and it's actually not a problem. The trick with doing math on a computer is that because of the limitations in how much room it has to store a given variable, so it can only store 15 decimal places. So if you write out a number to what seems like an obvious math problem, and it gives you something that seems weird, well, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 decimal places is exact. Everything beyond that's just the computer making up trash. So if you print out a number and it seems like it should be an obvious math problem and it's wrong after like 15 decimal places, it's just the computer screwing up rounding because it can't store that many decimal places. So that's just something good to keep in mind. All right. but that is only true of floats. Floats are the only variable that has decimal places attached to it. If I go back over to my little display here, go back over to my summary of data types, you see that the difference between integers and floats is that there are no decimals in integers, right? Integers are all exact numbers. Let's call it, it is 1, it is 2, it is 8, it is negative 432. They are exact numbers. It's the same as the mathematical definition of an integer. There are no decimal places in integers. It also means you can cheat a lot with the memory requirements of them. That's why computing 999, which is an integer, right, to the 1/1,000,000th power, the computer can do it, but it can also cheat and store it as a long or combination of longs, whatever. If we force it to use a float, 999.1, it limits it a bit. So it's easy to get the overflow error. Do you guys have any questions with this so far? Okay, I know this is some definitions that might seem esoteric, but it is good stuff to know. Cool, so we talked about this. And if you really want to know why you can only store variables that are so big, this is why. This is 999.1 stored in binary. Again, there's only so many bits that the computer can use to store a given number, and this is how it changes those bits, those ones and zeros, into a number with a decimal or whatever. So just a neat thing. Cool. The nice thing though about between integers and floats is that we don't have to worry about them too much in terms of specifying what we're using. Python does that for us based on what we put in. So that's a nice thing. We need to know what they are because they will come up in errors. They'll come up in our code. But we need to know how to read what the code says that it thinks we're doing. But we don't have to worry about saying this is called computer make this an integer or computer make this a float. It'll do all that for us. That said, it also means if we say, hey, if we ask the computer whether or not 1 minus 0.1 is exactly 0.9, the answer might be no. Because it's not, because if we use floats, they are not necessarily exact. So we'll talk about that as we go along. As far as non-numeric data types, specifically strings, something you can store characters in, just not do math with. We'll be talking about that. We'll be talking about that later on. We're specifically going to be talking about strings, as opposed to nuns or booleans. Don't worry about those. But we're going to talk about that in about a month and a half. So don't worry about it for right now. All right. In terms of declaring variables. So when we did that example, we used the variable name 1_variable. That is what's called that was our name for that particular variable that we used. We can literally name our variables almost anything that we want. We can make our names as long as we want. We can make them as obscure as we want. We can do whatever we want, so long as we use a letter for the first character. We can have numbers anywhere in it, but the first letter has to be a letter. You can't use spaces, punctuation marks, or math anywhere in the variable name. So no slashes, plus, minuses, space, asterisks. Those are all out. You can't use those in your variable names. Capitalization is very important index with a capital I is not the same as all cap index. It's not the same as all lowercase. Index, if index is my variable name, and no keywords. We'll talk about that in a second. The key thing with variables though, you're naming something to store a value that means something, either pressure, length, height, width, speed, whatever. Name it something that will mean something to you. So when you write, when you make a variable name, try to have a purpose for it and name it for that purpose that you know what's going on. Okay. About keywords though. So you remember our print command, right? Like print meant something very specific. Meant that if I write print, open paren, close paren, anything inside those parens, it writes to the console window, right? Print has a very specific meaning. As you might imagine, there are many variables there are many keywords that have specific meanings in Python. So you have lots of different functions. If I name a variable for the keyword, for example, if I could go into my IPython if I go into my IPython window, or in this case my command line, I say print equals 134, it'll let me do that. But now let's try to do hello world again. It says, what the crap are you doing? I can't, it's called print doesn't mean that. You're trying to call it, it's an int, right? And integer, right? Because we just said that, right? Print equals 134. 134 is an integer. It's saying I can't call an integer. I can't treat an integer like a function. You've just gotten rid of the print command. Congratulations. This is why we have to be careful about keywords. If you do this though, just close out, reopen, and everything will be fine. Okay. I'm gonna get rid of print. Now print should work again. There we go. So, I don't want that. I want that. Variable types. So what? So for keywords, print is one to do. He'll watchful for. If else, while, input, for. Those are all key. Those are all keywords. Okay. So just keep an eye on that. Also, underscores. You can put them inside of your variables, right? We had one underscore variable, and that was a valid legal variable name. However, if you put them at the start of your variable names, like if I make a variable that's underscore max, that's actually a reserved keyword for properties. So don't start your variables with underscores. Okay. You got all those? Any questions about variable naming? It's pretty much just use words. Start with words. You can use numbers at the end. You'll be fine. Cool. And don't use spaces. Spaces are bad. Spaces are very bad. There we are. Okay. I have a personal vendetta against single letter variable names because they're meaningless. My exception is when you get into loops, we'll use IJKMN a lot just to count things because it's easy and almost everyone does it. But that's an exception to the rule. So try to make something that's useful to you. Other things. Math, because this is what we're doing the most of. A lot of this is straightforward from Excel. Yeah, add, subtract, multiply, divide. Yes, that's easy. Like we did before, we also have exponentiation is now a double asterisk. Keep keep that in mind. You might want to write that down somewhere. These two other commands, the integer quotient and the modulus, those might be two new math operators that you haven't seen before. The integer quotient essentially just is division without a remainder, right? 3 divided by 2 would be 1.5, right? Unless I ignore the remainder, in which case my thing's just 1. Yep. The modulo is what is the remainder. For example, if I have x is 12, y is 5, x modulo 5 is 2, because that's the remainder. 12 divided by 5 is 2 remainder 2, right? So just two other things, just two other operators to keep in mind. The big one to remember though is that your exponent is now a double asterisk sign. It's not a upwards caret the way it would be in Excel. Also, as you go through, you might run into variables being integers or floats when you don't expect them to be. So you might lose, you might do something and go, hey, this should be an integer. Why are there decimal points? Or there should be a float. Why aren't there decimal points? Python fixed a lot of this when they migrated out of version 2 and went into version 3. So I don't think so. It shouldn't be a problem that you encounter anymore. But just in case, a rule of thumb is that when you do math, it automatically becomes the more complex variable. So if you do a float like 1.1 minus 2, the variable type that I get out should be what? So float minus an integer. If I get out the more complex variable type, which one would be the more complex variable between an integer and a float? Like which one would have? Yeah, exactly. Because you have decimals. So if I subtract a float and an integer, I'll get a float out. If I ever divide, the chances are so high that you'll get a float, it's crazy. So it just always becomes a float. But if I do an integer times an integer, 2 times 2 is 4, right? Exactly 4. So that 4 would be what? A float or an integer? Right. So that's that. Cool. All right. But sometimes we'll get a float, and all we care about is the integer. All we care about is a whole number, right? So how do we get that? Let's look at some functions. So if you go to your IPython console, you can go ahead and use, let's see, this guy, round. So round, open paren, 55.11, comma 1, close paren, and hit enter. See what happens to that. I'll mirror it here. So round 55.11, 1. What did it do? You can try doing 55.18 if you want. What is it doing? What is it doing? Yeah. All right. Let's have a look. Oh, so if you go, so if you go in here, you have to hit that green arrow for it to run. Oh, and if you don't tell it to print, it won't print. If you type it in here in your IPython console, then it'll just write it. Yep. So if you type it down all down there, you should see it just pop right up. Yeah, or write it all in there. Yeah. Yeah, yeah. So if you put it, so if you write it up here, yeah, it won't write anything unless you tell it to print. Print a specific variable. Here you don't have it assigned to a variable. So if you want to, like, say out equals round, blah 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 blah. But don't worry about that. Just write it over here, or for right now. And it's still running on some. Still running on some. On something. There you go. Try writing it now. Try doing round 55.11. Yeah. Comma 1. Close paren, enter. It's taking a while to chug through that. Eventually it'll come through with a thing, with the result of that. And then try it with round 55.18, comma 1, right? So working for, great. So what is that command doing? Yeah. Right. It takes the number on the left and rounds it to one decimal place. If I change that guy there, oops, sorry. If I change the second, if I change the second value there, it rounds it to 2 decimal places. Make it 4, rounds it to 4, except, well, it's all zeros after that, right? So it just keeps the number, keeps number here as is. So this is, so just as print was a function, round is also a function. It's another keyword that you can't use for a variable, but it's another word that it's another function that you can use to do crap. This one is a little bit different. It takes, instead of print, which takes one thing, round takes 2 inputs, right? It takes the number that you want to round and takes how many decimals that you want to round it to. You can also play this game with the int command. So if I do int, say 55.18, I get 55. If I get int of all that, I get 55. If I do int 55 point whatever the heck I want to put in here, I will get 55. Every single time. What int does is it makes an integer out of whatever you stick into it. That's all it does. So it just takes the number to the left of the decimal point, chops off everything to the right, and just keeps that. So just different functions that you can use to change floats and ints and stuff. Okay. Hope that's not too nutty. Okay. Jump back over into this. Before we get too far off track, though, let's get back to talking about math. So, variable types, that one. There we go. All right. So if you remember PEMDAS and order of operations and stuff, order operations is a big deal. So for example, I have this math problem that I have in code, right? This is my math problem. I have a whole bunch of different variables here. I have reservoir max depth, reservoir min depth, multiply those by reservoir width times reservoir length times this times blah, blah, blah. What's going to be the first thing? What's going to be the first bit of math that this thing does. Right, and this is what it's called, and this is the point. You have to think about it a little bit, right? Because you go, okay, where the crap are the parentheses is here. So if I go through, it's, hey, do what I ask you to do. Thank you. It'll do that part first, then it'll do all those multiplications. That'd be a pain, but it's a pain in the butt to figure that out. And if I screw up a parenthesis, I'm dead. So how I'd recommend doing math in Python is not all on one line like this. Do one thing at a time, especially things that make sense. So like if I look at, say I'm looking at a underground reservoir, right? Look at the maximum depth and the minimum depth. That gives me like a, that gives me like a thickness, right? So I call it a depth of the pair, and I can save that to a variable. A width times a length is like an area, right? How much it holds is porosity times saturation. Then I can just multiply those three together in a very, very simple problem to get my answer. Do you kind of see where I'm going at here? It's if you've ever typed something wrong into your TI-80 89 or Excel, you know how annoying making a one single line math problem is. My advice is don't do it because it's a pain in the butt for everyone involved. Split it up so that you don't get screwed up by order operations. All right? Cool. All right, cool. So with that, we have a quiz. So what kind of variable type would I use in order to store those numbers? 0, 2, 3, 4, 123, negative 435. What variable type would I use to store those? Yeah. Yeah. And then how about pi? Yeah, exactly. Great. Easy quiz, right? Now for the better quiz. We're going to code. Game on. So the first code's relatively straightforward. Let's get to work. We're going to take two numbers, add them together, and we're going to print them. Should be straightforward. Let's give it a shot. Okay. Do I have Vim on this? Should have Vim. There we go. Okay. This is my bid for a editor that's not Spider. So I'm going to make a code that grabs two numbers, adds them together, and prints the output. So I'm going to start my code with a comment saying this adds two numbers together and prints the output. Remember to put a hashtag # comment sign at the beginning of that line. All right. Then I need two variables. I'm going to call my variable x because that's a good eponymous one. I'm going to call it 1.5 for right now. Does it matter what I call it? No. Let's say first variable, change as needed. So when I run this line, x takes on the value of 1.5, and then I add a comment right after that. So the computer ignores everything after that comment sign, right? So it does that and moves on. Second one, let's call this 4.5. Say this is my second variable, change as needed. Oops. And make sure that I am actually sharing this screen. There you go. Sorry about that, you. All right. So I need to add, to add them together now. I'm going to save, I'm going to save that output as answer. And then I'm going to print the answer. All right. Any questions on what we just did? Does that kind of make, does what we just did make sense? We named two variables. We assigned, which is called by assigning values to them. We added them together, assigning that sum to another variable, and then you print that, which is called that output. Note that I can't just do this because you're saying x plus y. You're not telling it to put that anywhere. It has to put it somewhere, and that's why we had that. That's why we assigned it to a variable. So if you run that, so my code's called first addition.py. I have to do this because I'm not in Spider. You should see 6.0 pop up in your IPython console. See? It'll say, I don't know what the heck you're doing. Yeah, everything on the right is stored on the left, always. Everyone get something that runs? Sweet. All right. And now now kind of the beauty of code is that if I go back into this, I can adjust those numbers to whatever the heck I want. Run it again, and it'll just say, okay, I have new numbers now. Here's whatever my new answer is. This is the kind of the beauty of code. You don't have to have one. It's not like solving through a math problem and coming up with one answer, and then if you change the number at the start, you have to like resolve it all. You're coding in an equation that you can use for anything. Just the sweet part. All right, so that's problem one. Problem two. Okay, the Fibonacci sequence, right? You guys good? Say again? Oh, you see that? Yep. You're good. Okay, so next thing that we're going to try. It's a little bit more complicated. We're going to try to write the first 5 digits of the Fibonacci sequence. You're going to see a lot of sequences in this class because I think they're cool and they're really easy to practice coding on. So, cheers. Does anyone know what the Fibonacci sequence is? Okay, so the Fibonacci sequence is a sequence of numbers. That's this. That's the first one is 1. Second one, it's going to be easier if I just write it on the screen. Oops, not that way. Clear. Give me some text and make it white. Okay, so 3, 1, 2, right? 1, 2, 3, 5. Yeah, it'll come up in a second. 13. Okay, so those are the first 7 numbers in the Fibonacci sequence there. 1, 1, 2, 3, 5, 8, 13. But it's a sequence. There's a pattern to it. What's the pattern? as a hint, the sequence starts with those two numbers there, 1 and 1. If I start with those two numbers, I can get the next number and the next number and the next number and the next number. Yeah. Yeah. Exactly. If I take 1 and 1, I get 2. If I take 1 and 2, which is my next two numbers, I get 3. Take 2 and 3, my next two numbers, I get 5, and so on and so on and so forth. That is the Fibonacci sequence. So what our code is going to have to do is that it's going to take two numbers, add them together, you get a third, add another number, get another one, and so on and so forth. Okay, so let's do that. So if I, whoops, back to the mouse. Okay, so I'm going to go back into here. I'm going to delete all this. Okay, so my new code's going to compute the first 5 values in the Fibonacci sequence. All right, so and my first value is 1 and my second value is 1, right? That's where I start, and that's where I start from. So here's var1 and var2. That's where I start my Fibonacci sequence from 1 and 1, right? Great. All right. So we said that in order to get the next value in the sequence, I just add the last two together. So if my next value is next var, var1 plus var2, right? That's my last two values in the sequence. I just added them together and stuck them into a new one. Cool. So that gives me my third value, right? How do I get my fourth one? If I can write. How do I get the fourth value? Okay, yeah, because this is my first value, this is my second value, this is my third value. The fourth value is the third value plus the second value, the last two, right? So all right, that is one entirely valid way to do it. Here's another way. As we start to think of, and I'm just going to comment that line out. I just put a pound sign at the start of it, so the programming ignores it. As you start to think about code, you want to start thinking about trying to do things more efficiently, using less variables to the same thing, or using less variables because we can only assign variable names when we're typing things in, right? So Jenna, the way that you said is perfectly fine. It's perfectly correct. It'll do exactly what you're saying. But another way to do it is just say, well, let's say let's call var1. You can say that that's like the value 2 values ago. var2 is the value 1 value ago. The next var is the value that I'm on. So I can say, I can just bump everything back by one value. Does that make sense? What did I just do there? Say again? Right. And this is when I say when I say efficiency, this is kind of what I'm talking about. I can keep on making up new variable names, but if I just copy these 3 lines of code, the sequence will just continue and continue and continue and continue and continue. I don't have to do anything else. I just pull those three lines, and so long as I just keep copy pasting them, I can just keep on continuing the sequence as long as I wanted to. Because here, if we start looking at this, var1 is, if I go back up to line 6 here, it's 1 + 1 = 2, right? Well, when I take var2, put that into var1, so that's 1. Next var is 2, put that here, so that's 2. So this is now 1 + 2 = 3, right? Then I'm kind of shift everything back again. I take var2, I put it into var1, so that's 2 now. Next var2, that's 3. 2 + 3 = 5. And so on and so forth. And remember, my Fibonacci sequence is 1, 1, 2, 3, 5, right? So this is so if you start thinking about patterns and how you can leverage those patterns, you can start to make some really kind of neat bits of code that do exactly what you want in a very, very straightforward fashion. Now, a problem you guys might be experiencing if you're doing this in the scripting window is that it's not printing anything, right? Why? Why isn't it printing anything? Right, we didn't tell it to print. And this is probably the single most aggravating part of coding. The computer will do exactly what you tell it to and nothing more. So if you don't tell it to print, it won't print. So let's print. We want to get every single value here, right? So I'm going to tell it to print var1, print var2. Okay. Tell it to print next var. I'll tell it to print next var every time that it computes a new value for next var. All right? Then if I run that, should get something that looks like that. Yeah, get anything good? So you want it to print every new one. So just tell it to print next var. Every new digit in the sequence you want it to print. Yeah. Yeah, and then you can just copy. You got it. How you guys doing? Is it doing good? Is it doing good things? Cool. All right. Doing good things for you, Brandon? Right. Cool. Yeah. Cool. All right. And if you wanted to do the next 20 digits of the Fibonacci sequence, you could just copy paste that ad nauseam. Any questions on that? No? Okay, great. All right. Then let's call so the last example here is to write out the first 5 numbers of the Fibonacci sequence from an arbitrary integer. So instead of 1, use some other number. How do we do that? How do we change what we just did in order to start from an arbitrary number instead of just 1? Yes. Yeah, it's called yes. So up at the top of our code, where we said what var1 and var2 were? You just change that, because all the math's set up, right? Here we should just have to say I want it to be 5 and 8. There you go, done. And that's coding. Any questions? That's kind of all I have for today. Okay, so I have a question. What is this class going to look like? So, so Fridays are the quote-unquote lecture day. Today is the lab day. We just ended up starting on the lab day because for whatever reason they put it first. So hey, we're here. Usually what's going to happen on a lab day is there'll be some problem that'll have some practice thing, or if you guys have something that if you want to go over from the homework or whatever, we'll kind of code through it that day. Everyone can kind of do it at their own pace. I'll just be doing it up here with whoever wants to do it at the same pace as me. On Fridays, we're going to talk about some part of the language. That's what we're talking about. This Friday, we'll talk about decision making. So if statements or conditional statements. That's what Fridays will be for. Mondays will be kind of the play day, if you will, because nothing's more fun than playing with code. So that's kind of what it's going to look like. I'll have homework for you on Friday to kind of practice with the language, get familiar with it more. I hope that this is a pretty straightforward introduction. You guys feeling pretty good about things going forward? Okay, cool. Okay, great. Yeah, Friday will start kind of more of the work, and we'll be progressing towards making tools. Thanks for stopping by.